Hello, and welcome to this discussion on the advancements the ESA is investing into their precision portfolio. My name is Daniel, and I will be your navigator as together we further investigate the supreme high ground, outer space. And now, with no further ado, let's jump right into and explore what's cooking over in Europe. In our discussion, we'll explore the new and innovative approaches that currently are being developed to support the European Space Agency's Galileo constellation. Specifically, we'll dive into the agency's FutureNav program to include its portfolio, specifically discussing its current efforts with both the Genesis mission and the LEO PNT initiative. The Global Navigation Satellite System plays a significant role in various aspects of modern society. Their capabilities encompass applications such as navigation, mapping, scientific research, and emergency response. It provides reliability and accuracy for industries including transportation, agriculture, the communications, and supports routine activities like route planning and local based services. As global connectivity continues to grow, there will be a greater need for reliable positioning and timing, which makes GNSS essential for both economic and social activities. Innovations and technological advancements to GNSS aim to address current limitations and introduce new functionalities. Recent developments in signal processing, satellite design, and error mitigation have contributed to improved accuracy, greater resilience to interference, and a better coverage in various environments. Several countries operate their own GNSS, as we can see in the picture on the left. The United States runs the Global Positioning System. China uses the BeiDou system. Russia operates GLONASS. And the European Space Agency oversees the Galileo constellation. Although each of these countries continue to invest in advancements for their respective systems, the ESA is making significant investments within their Future Nav program. In 2022, ESA launched the Future Nav program with efforts to consolidate initiatives in gathering market intelligence, setting R&D priorities, exploring modern technologies, refining existing concepts, and building their industrial capacity. Under this program, the first two mission portfolios are under development. The first is Genesis, an effort to combine the four geodetic techniques, enhancing global reference framing into a singular satellite, a feat which has not been yet accomplished. The second is a low Earth orbiting position, navigation, and timing, or LEO PNT demonstrator constellation. It's aimed at presenting the advantages of having navigation satellites in low Earth orbit. Now, each country that operates a global navigation system has developed its own independent terrestrial reference framing systems. However, all of them utilize the same set of standards, which is identified by the International Terrestrial Reference Frame, or the ITRF. The ITRF is a globally recognized standard for precise positioning that fortifies natural geodetic systems and is the meteorological basis for all position-based information, such as mapping and 3D modeling. It supports critical activities like land surveying, navigation, and climate change monitoring by providing accurate observations of slow Earth processes. The ESA specifically has developed their reference frame called the Galileo Terrestrial Reference Frame. Again, this reference framing system follows the international standard. The overall mission objective for Genesis is limited to just one: to attain an ITRF accuracy of 1 millimeter, with long-term stability maintained within 0.1 millimeters per year. The $76.6 million euro mission will have an eccentricity of 0, an inclination of 95 degrees, and will operate at an altitude of about 6,000 kilometers. Its platform includes a ground control segment with a mission control center and ground stations, a dedicated data processing center with a global GNSS sensor network, a data archiving and distribution facility, ground infrastructure, and the satellite itself. The satellite specifically includes a GNSS receiver, a very long baseline interferometer or VLBI system, a single lens reference camera or SLR, a Doppler orbitography and radio positioning integrated by satellite, commonly known as DORIS, receiver, and will have a mass of approximately 300 kilograms. What's the significance, you ask? Well, although an increase to the constellation's current 3 to 5 millimeter reference frame provides negligible significance for navigation, any improvements to further increase, rather reduce, the millimeter base is especially important for geological monitoring and for orbital location precision. This level of precision will enable the detection of even the smallest minute variations in the Earth's solid, fluid, and gaseous components of its core. This mission will ultimately enable ESA to strengthen the connections between the ITRF and the International Celestial Reference Frame by improving the determination of Earth's orientation parameters. Next in their Future Nav program is a newer initiative called Low Earth Orbit Positioning, Navigation, and Timing, or LEO PNT. The LEO PNT initiative is serviced by two contracts, each worth 78.4 million euros. Both contracts articulate the development of two end-to-end LEO PNT demonstrators. The contract deliverables include the satellite themselves, payload design, ground segments, user testing, launches, its operations, and of course service demonstrations. This will enable both contractors to partner with over 50 entities from across 14 countries, spanning both already established space firms and innovative newcomers, to launch the first satellite within the first 20 months of the project commencing, with the full constellation to be expected on orbit by 2027. The constellation parameters encompasses 10 demonstration satellites orbiting at about 510 kilometers and designed to test signals across multiple frequency bands. The constellation's configuration will be two Pathfinder A satellites, one which will be operational and the other will be the spare, and 8 Pathfinder B satellites. The initial deployment of satellites will be the Pathfinder A, which will be a small CubeSat about the size of a suitcase with a mass between 20 and 30 kilograms. Subsequently, the Pathfinder B satellites will be much larger in comparison and extraordinarily complex. The mission objectives for LEO PNT will assess how using a multi-layered approach could improve the interoperability robustness of the Galileo constellation and other global navigation satellite systems to the existing medium Earth orbit GNSS signals. The program will also seek to provide services in areas where current satellite navigation has limited coverage, such as urban environments and indoors. A third objective for the constellation will be to assess its interoperability of PNT with other communication standards up to 6G, which may present favorable opportunities for other programs, applications, initiatives, emergent services, or low latency data for positioning and timing like transportation, which would include automotive, autonomous vehicles, rail, and maritime vehicles, digital mobility, critical infrastructure, mobile devices, asset tracking, and indoor positioning. The LEO PNT will use Rocket Lab's Electron rocket for the dedicated launch from a New Zealand launch facility with a target date of mid-December 2025, and as mentioned before, with a goal of having the entire constellation orbiting by 2027. To wrap up, the Genesis mission represents a significant leap forward in pursuit of ultra-precise geodetic measurements and global navigation capabilities. By integrating all four major space-based geodetic techniques, GNSS, VLBI, SLR, and DORIS, into a single satellite platform, Genesis is set to refine the international terrestrial frame to extraordinary levels of accuracy, targeting, millimeter precision, and remarkable long-term stability. In parallel, the Low Earth Orbiting Positioning, Navigation, and Timing initiative promises to transform the landscape of LEO satellite navigation. Together, they both demonstrate the European Space Agency's commitment to advancing the state-of-the-art in positioning, navigation, and timing. By fostering interoperability, precision, and resilience across global satellite constellations and terrestrial reference frames, these missions will reinforce the foundational infrastructure of modern navigation, Earth observation, and science research. Well, everyone, this concludes the session of Advancements in Space. Until we meet again, my friends, continue exploring.